Here we are with Newton's method. This is going to be the method to approximate x-intercepts, or really just solutions to some equations. We notice that solving these equations here are pretty important. The first one helps find us x-intercepts. The second one helps us find critical points. This third one with the second derivative helps us find those important points, we called them, the ones that maybe could be inflection points. So sometimes these equations end up being really hard to solve. Let's take a look at one that we've seen already that is hard. This function x plus 2 cosine of x is one of the ones that we had in our homework that we found was just difficult to find the x-intercepts of. It's impossible. So for something like this, we could start by looking at our graph and saying, well, our x-intercept looks like it's, maybe I give a bad approximation. I say, oh, it's close to an x value of 0. Now, obviously, that's not right. It's closer to -1. But let's start at 0 and see what happens with Newton's method. What Newton's method is going to do as we drag our slider here is it's going to first create a tangent line using the derivative, and it's going to find the point at which the tangent line crosses through the x-axis. It's going to figure out what that x value is, and it's going to take a look at the function at that x value. Then, as we keep stepping through here, we'll do it again. We'll take this point, come up with a tangent line, find out where that tangent line crosses through the x-axis, and come up with that x value. So here, our x value keeps changing as we step through Newton's method here. I can zoom in a little bit so we can see what's going on here. Maybe I'll step this back a second. All right, so here our old tangent line crossed through at negative 0.995-ish. And so we figure out where that point is on the graph, build the tangent line there. That's kind of hard to see. It's a little darker. And that's going to cross through right here. And so that's our new point. That point's really, really close to the actual x-intercept, and this one is even closer. But you'll notice that if you zoom in really far, now we've got to zoom in really, really far to notice this, it's not going to be exact. But as we keep zooming in, we get this nice local linearity. So I'm probably going to need to zoom in a long way before I can tell that that's actually different. So this is a really good approximation of all this stuff. So if I zoom it out now and get this back to my regular picture, we might be able to see what could happen if we picked a different starting point here. Oh boy, this is taking a long time. I shouldn't have zoomed in that far. So now, instead, we're going to back out of Newton's method here, and we're getting back to normal. Let's back that all the way out. And let's start at an x value that's farther away. Let's start at an x value of like 1.5. Notice that we're on the other side of our little hump here. When we create tangent lines, they're not going to be pointing towards the x-axis, or the x-intercept, sorry. And so the points that we find if we step through Newton's method aren't actually going to be x-intercepts. So that's a kind of a problem. That just tells us we need to actually start close-ish to the x-intercept. Anyways, here's what Newton's method actually is. It's this little algorithm. We pick the starting point, and we want to make sure it's relatively close to the x-intercept. Then, every time we want to find a new point, we take our starting point, or the point that we're at, and we subtract the function divided by the derivative at that point. Make sure that our derivative is not 0, or else you're going to divide by 0. And then if you want another approximation, you'll say, okay, take the number you just found, make that your old x, subtract your function over your derivative. Grab your graphing calculator, and we can start figuring out for this function. So here, our function is this cubic polynomial. There are 3 x-intercepts. These are not them. These are just values that are close to the x-intercepts, because the x-intercepts are at these weird irrational values. So this is something where it'd be like really hard to figure out what they are. So if we pick our starting point at -3, after the first step of Newton's method, we get -2.667. And after the next step, we're at -2.604. And after the next step, we're at -2.602, etc., etc., etc. Again, for each step, we're going to take our old x value and subtract the function over the derivative. So go ahead and grab your graphing calculator and take 0, maybe I'll write this down here, minus 0 cubed minus 6 times 0 plus 2, all in parentheses, over your derivative evaluated at 0. If you do this, you're going to get a third. Maybe if I just round that off to 3 decimal points, I've got 0.333. Now what you're going to do is you're going to take 0.333 and you're going to plug that in here, 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 and here. So you're going to take this new value that you've got and put it in place of 0. A nice little hint on your graphing calculator, you can just hit second, enter. It's actually called entry as the second function, and that'll spit out all the stuff that you just typed in. So now you can go ahead and just go change 0 to 0.333. And if you do that, you're going to get 0.340. And now if we take this value and plug it in place of all the 0.333, we just end up with 0.340 again. And we get the exact same thing for both of these steps. So maybe 0.340 is a pretty good approximation of what's happening. Go ahead, try with this x value here, starting at 2, and see what kind of answer you get. Pause your video and go along with this example. See what kind of answer you end up on this last one. I'll put the answer here when you come back. After 5 steps, if you round this off to 3 decimal digits all along the way, you end up with 2.262. So we've got 3 x-intercepts. That's a pretty good estimate of it. That's a pretty good estimate of it. And that's a pretty good estimate of it. Now, how good is pretty good? That's the main question here, right? When do we stop? How many estimates are enough? There's a couple of different versions of this that we can do. We can sometimes just be told to do some number of steps. That's like what we did up in that last example. We did 5 steps of Newton's method. So do 5 approximations and then stop. Sometimes that's good enough. So if you're told to do a certain number of steps, do that many. Sometimes you'll be told to find it accurate to 3 decimal places or 4 decimal places. Meaning every single time you do it, you're going to round off to that many decimal places, and then you can stop once you get a repeat in your answers. Notice here, we got a repeat of negative 2.602. And over here, we got a repeat of 0.340. And over here, you did get some repeats of 2.262, sorry. The key here is once we would get this first repeat, once we see, oh, negative 2.602 is the same as this last step, we could stop because we're going to keep getting the same answer. And after our third step on this x-intercept, we can say, oh, we repeated our answer, let's stop because it's just going to repeat again. So round it off to however many decimal points along the way and then stop once you start getting some repeats. That's one of our strategies. The last one that we can do is we can try and get it really, really close, and we'll have some number that says this is close enough. That number is going to be called the residual. Basically, what we can say is that our approximations of x-intercepts are not actually x-intercepts. And so to find out how far off they are, we can just check the height of them. We can go ahead and take our best approximation that we found, plug them into the original function, and since they're not actually x-intercepts, we'll see what the actual height of the point is. It should be pretty small. It should be close to 0. Sometimes we'll give a boundary on how small that has to be, and we'll say, okay, make the residual smaller than 0.01. And so as long as you get an x value that the height is smaller than that, that means it's close enough to the x-axis for us to stop. So 3 different ways of doing it. Sometimes we'll just be told a number of steps to do. Sometimes we'll be told to approximate it within a certain number of decimal places. And sometimes we're going to try and make the residual small enough. Here's another example that I'll set up, and we can just kind of start it, and I'll leave you to finish it. We want to find the intersection point between these 2 graphs, which is the same as taking a look at the difference of the 2 and then setting that equal to 0. So what we're really trying to do is solve sine of x minus x plus 1 equals 0. If we go ahead and take a look at the graph of sine of x minus x plus 1, let me pull that up real quick here. If we graph this thing, it's going to look like there's an x-intercept somewhere close to 2. And that's good enough to say. We'll say, oh, it's close to 2. So we'll say, all right, our starting point is 2. Now, again, each time we find one, a new point, we're going to be looking at the old x value minus the function over the derivative here. I always mix these 2 things up. Make sure that you know the derivative is the one on the bottom. So we can say, all right, maybe x1 is going to be 2 minus f of 2 over f prime of 2, where f prime, or sorry, I should say h, or say h prime is going to be cosine of x minus 1. So we'll go ahead and plug 2 into all that stuff. So we'll say this is 2 minus, in parentheses, sine of 2 minus 2 plus 1 over, in parentheses as well, cosine of 2 minus 1. And that gives me 1.93595. And since we want to go to 5 decimal points, that's where I'll leave it. For my next one, for x2, I'm going to say 1.93595 minus, sorry, I should say h again. I keep writing f instead. Minus h of 1.93595 over h prime of 1.93595. And we can just keep plugging things into this function here and this function here. Go ahead and do that until you find a number that repeats. That's going to be a pretty good solution to this equation. So as long as you remember this form here, everything should go pretty well. Newton's method of approximation is very algorithmic. The nice thing about this is you can use this little GeoGebra applet. You can change the function here. So if we want, we can go back and say our function was sine x minus x plus 1. Let's type that in here. So let's get rid of this one, and we'll say, oops, sorry. We're going to say sine of x minus x plus 1. Here's our graph. Let's start around 2. Our first step is going to be that 1.93595. And you can check your answer on here. And notice that it just changes a little bit, and after that, it should start repeating. So you should find that your second step will be different, and then your third step will be the same thing. So then you can stop, because it's going to be rounded off to 5 decimal points. So this should be what you get. Make sure that you go through your calculations and see that, but Newton's method isn't anything much more than that.